Recording. All right. It is a real pleasure to introduce Julian Pearce of Cardiff University. Julian completed his undergraduate studies at Cambridge and completed a PhD at the University of East Anglia. Julian has spent his career at the forefront of geochemistry with academic appointments spanning the Open University, Newcastle, Durham, and Cardiff, where he is now a professor emeritus. He is known for his work in geochemical fingerprinting, ocean drilling, and large-scale geochemical datasets, and has played major leadership roles in both ODP and IODP expeditions. Julian has supervised more than 30 PhD students, published over 130 research papers, and has had his work cited more than 80,000 times. His contributions have been recognized by multiple awards from the Geological Society of London. Today, he will talk to us about the geochemical fingerprinting of Earth's oldest rocks. Please join me in welcoming Professor Julian Pearce.
Okay, well, thank you very much for the introduction. The title, I think you already know. I'm looking at the fingerprinting of the Earth's oldest rocks. What I'm specifically doing, I got inveigled by Michael Brown into writing a paper with him on whether plate tectonics is a post-Archean phenomenon, a petrological perspective. And the idea was that I wrote the igneous part and he and Tim Johnson wrote the metamorphic. And the idea was to look at these together. And this was published about a year ago. I haven't actually talked about it yet in public, so this is my first effort, and we'll see how it goes. I won't be able to talk about all of it, but I'll talk about what I think are some key interpretations. First of all, I guess something about fingerprinting, as people may know, I've spent a lot of time geochemical fingerprinting, and I thought I'd just start by saying how I do it in post-Archean times. And the way I do it in post-Archean times now relates to something actually done with Richard Ernst on lip printing, but it works also for fingerprinting plate tectonic settings. It is to look at a set of proxies, where each proxy relating to a particular process and the proxies in question being effectively orthogonal. So in this particular case, I look at crustal proxy, which tells me about subduction, crustal input into a magmatic system. So it tells me about subduction, it tells me about subduction modified lithosphere, and it tells me about crustal assimilation. I look at, and that's thorium niobium, which they behave in similar way in basalt genesis, but different way when we have crustal melting and crustal involvement. And then we have a melting proxy, which is titanium over ytterbium. Again, they behave in similar way unless garnet's involved. Garnet tells us about depth of melting and degree of melting, so that's a useful proxy, and that tells us about melting in an igneous system. And then it's very useful too to have a fractional crystallization proxy so that these other processes can be fitted into the crystallization system. And so I use here typically decrease in nickel as it reduces in concentration particularly fast when fractional crystallization is taking place. So there's the proxy there. And to do the fingerprinting, then I have a set of projections, and each projection helps to interpret the tectonic setting. Here's just an example I know, which is AFAR. Here's the crustal proxy. Here we have the region for no continental crustal input. Here's crustal input by subduction and other methods. AFAR plots primarily in the area of mantle plumes and asthenosphere, indicating either an oceanic setting or a continental setting. But this trend here towards crust, which we also see here, tells us we've got a continental plume setting with interaction with crust. And then these melting proxies tell us about the degree of melting and tell us that with time, degree of melting has decreased, which is consistent with a plume head going to a plume tail. So we can do all this in the post-Archean environment. However, when we come to the Archean, certain differences make this precise method difficult to directly apply. And one of the big differences is in the mantle potential temperature. As people know, there are lots of there are lots of models for this, but most of them have temperature increasing with increasing age, and also a big range of melting temperatures from komatiites through to basalts. And this effectively makes it very difficult to use a melting proxy, at least routinely. And it also means because komatiites up here pour nickel into the crust, it means this isn't a very good discriminator. So as a result, for working on the Archean, I'm restricting this to the crustal proxy, and I'm restricting this to a different fractional crystallization proxy, which is scandium in this particular case. So here then is the basic idea. And so we only have two proxies here, but nonetheless we can tell an awful lot from them. So with a crustal proxy, here's a crustal proxy diagram. The proxy itself is diagonal, and ytterbium is a useful normalizing factor. And so we have this Morb-Oib array, which is going to tell us about Archean environments where there's no crust involved. And then here is the arc or crustal array, which will tell us whether continental crust is involved, whether there's subduction involved, or a metasomatized lithosphere involved. And you'll see from this that here's where continental crust plots, and here's where arc plots, and you can see they overlap. And so this crustal fractional crystallization proxy enables us to distinguish from subduction zone added and then crystallization, or no subduction zone and crystallization. So the combination of the two is very important. Oops. Sorry about this. Oh, there we go. The question then is, how robust is this? And it's really critical that the crustal proxy is robust enough to deal with what's happening in the Archean. And one thing you can see here, what I've plotted is the typical crustal contaminant. Here's felsic continental crust from the Phanerozoic. Here's Archean felsic continental crust, and you can see they're more or less identical. So there's going to be no difference in crust that's going to, between the Archean and present day, that's going to affect the fingerprinting. Also, if we talk about potential increased subduction temperatures, here's what happens in subduction. Initially, nothing, no thorium or niobium are released. Then thorium is released. Then thorium and some niobium is released. And that's with increasing temperature. So if we increase the temperature more, we're going to get some niobium as well as thorium being mobilized. And that means that the vector is cold is more or less a vertical vector, and then the hotter it gets, the more diagonal it gets. But nonetheless, it still occupies the arc field, and so it doesn't affect the fingerprints. And this is a very interesting one because crustal growth has a little effect, has a small effect on the Morb-Oib array. If we go to primordial mantle, and we had a mantle array at that time, this array here would be displaced so that that would be in the center. Here's the present day mantle, and here's the array now. In Koronaga's model, all the crust is all the crust is grown before the oldest volcanic rock, and so that doesn't matter. The mantle goes from here to here before any volcanic rock is erupted. But if we take some of the other models, then one would need to think that there might be a slight difference in the Morb-Oib array with time. So that's quite an interesting one, and everything I think so far points to the Koronaga model being correct, but nonetheless it's something to think about. Okay, well excuse me here, back to the Brown et al. Paper then. What I did for this was produce a fingerprinting flowchart which identifies routes which need to follow in order to have potential plate tectonic indicators. And the indicators here are indicators of active subduction, inherited subduction, because that still means there's been subduction at some point in time, and the formation of oceanic crust. And very quickly, the way I've done this is start off with the crustal projection, which is this, and then note that the subduction interpretations require high and consistently high thorium-niobium ratio. The ocean crust requires no continental crust, so it requires a low ratio. And if you have a mixture of low and high ratios, then that is typically plume interacting with continental crust, in other words, plume-crust interaction. And typically the intermediate one will lead to a no plate tectonic situation. The high value will lead to potential subduction, and the low one will lead to potential ocean crust. But it's not totally that simple. There are overlaps, and one needs a series of decision points in order to fully decide whether this signature really is of a subduction process or whether it involves, for example, it's really a mantle plume that's had a lot of crustal input. So that's the basic idea. And what I'm going to do, I haven't really got time to talk about all of this. I'm going to check the time too. I haven't got time to talk about all of this. But what I'm going to do is to specifically talk about this route, which is the route to active subduction and inherited subduction, and go through some examples and come out with some conclusions about there must have been some active subduction of some kind, not necessarily plate, but some kind, and there's an awful lot of inherited subduction in the Archean geological record. So let's have a look at this. And I'm going to start by looking at Pilbara in Australia, because I think that's one of the really nice examples of going from lips through active subduction to inherited subduction in kind of one craton. I'll then look at the Bushveld and the Kopfval craton, where I can find inheritance signatures but no arc, indicating that there possibly is an arc, if you like, beneath the surface. And then I'll look at Navruagituk, if that's how you pronounce it in Canada, where we've got ultra high grade metamorphic rocks, and try and demonstrate that you can see through that and see the subduction process. So let's start off with the Pilbara and the trend from lips through active subduction to inherited subduction. And here's a Pilbara terrain. We have an East Pilbara terrain, West Pilbara terrain, Mallina Basin. The whole sequence comprises something over 0.5 gigayears, 500 million years. And so it covers a large part of the Archean, and this is what I'm going to have a look at. There's a lot of nice papers on this. I haven't cited them all here, but I'm sure they're easily accessible. Anyway, here is the picture of a section through the East Pilbara terrain, which takes us down to about 3,200 million years. And there are alternations in this stratigraphic section by Van Kranendonk and others between the green, which is basaltic magma, the purple, which is komatiite, and the yellow, which is felsic magma. And we see that very classic field localities of the purple, komatiites, the green, bastic lavas, and the yellow, which are the felsic volcanic rocks. And if we look at these on the crustal diagram, starting off with the green, what we see is a trend which starts in the plume or Oiberei, Morb Oiberei here, and heads on a vector towards Archean felsic crust, which I've put in as the local TTG composition. So these are typical continental tholiites then. They're intraplate, plume-related, no obvious subduction component, and they've interacted with crust, and that's the green on this diagram. If we then look at the evolved volcanics then, what they appear to be is a continuation of the green trend. But it's not totally simple that they're an extension of that trend. But that is one option. So it is quite possible this plume, the plume has interacted with the crust, it's melted a lot of crust, and you get a complete sequence from plume right through to TTG. So that's one option, and one might imagine it's the obvious option. But Barley and a number of others have pointed out that maybe the yellow represents arc sequences. So what the Pilbara contains is a sequence of plume arc, plume arc, plume arc, a kind of model that has been very popular in the Superior Province in Canada, in fact, for rather younger rocks, but an alternation of plume and arc. So the question is, can we distinguish that? And here's the plume arc model then, that rather than having assimilation and fractional crystallization going the whole way up, that argument is we have a subduction trend, which being Archean will be rather hot, so it's at an angle. And then we have assimilation and fractional crystallization leading from a subduction component. And the question is, how do we distinguish these? And this is a very important thing to be able to do. And as I pointed out earlier, I want to use a fractionation proxy for this. Nickel and cobalt are just problematic in the Archean because there's so much in the crust. And so, as I reported before, I'm using scandium. And here are modern examples of how scandium against the crustal proxy thorium niobium can be used to distinguish these two options. So here we have a series of different types of volcanic arc. They're fractionated from pickrite to basalt, basaltic andesite, andesite, dacite, rhyolite. These are the trends. So if we have high thorium niobium acidic compositions, we can see they extrapolate back into the arc field. If we take plume magmas, which also have evolved rocks, as in Nemrut Mus in Muş in Turkey and the Yellowstone, they also have high thorium niobium ratios, but they extrapolate back into the Morb Oib array, showing that they're fully crustal interaction. And so this diagram helps to distinguish between the two. So what about the Pilbara group then? Well, what we see is here's the trend. These are the yellows, these are the greens on that diagram. And if we follow any one of them, like the red one, we can see it extrapolates back in, if we go down to pickrite, it would extrapolate back into the Morb Oib array. So essentially, we would interpret this, I'd interpret this as an intraplate anorogenic setting, and the yellow is part of the crust plume, if you like, interaction. So a Yellowstone model would very nicely explain this then, getting large amounts of felsic rock periodically within an anorogenic lip setting. Okay, so if we now go to the West Pilbara terrain, then we find a completely different sequence. There's been some nice papers written on this. I went there once, not to see very much, but there's a picture from it. And this sequence over here is quite different from the East Pilbara sequence. And we can see it here from Smithy's work. It's a sequence here which is over 10 kilometers thick. It has a range of rock types, tholiites, boninites, calc-alkali rocks, rhyolites, and they vary systematically with depth or with altitude in this sequence. Tholiitic more in the center, boninites and calc-alkali rocks at the base, and more calc-alkali rocks at the top. And here's where they plot on the crustal proxy, and you can see, again, there is some form of ambiguity here. Here's the upper and lower sequence, here's the middle sequence. And so we need scandium to resolve this. And this is what we see. So the lower and the upper sequence then, the evolved rocks have high thorium niobium ratio, but when you extrapolate them back, they plot clearly in the arc array. The middle ones plot in the Morb Oib array. And so what they indicate or what they support is that you've got some subduction, possibly and likely a volcanic arc seen at the early and late part of this, and then something much less subduction-like, if you like, in the center. It's extremely interesting as to what that represents. I mean, I would agree with people here who don't want a very stable subduction system, and subduction that starts and then you have a break off of a slab or something like this would fit in very nicely with this sequence. So here's the difference then. Here's the anorogenic sequence, no plate tectonics, if you like. Here's the more orogenic sequence, possible plate tectonics. And then we come to the Malina Basin in the center here. That's a typical sedimentary basin, nothing exceptional about it in terms of its structure and distribution of magmatism along faults. But when we look at that in the fingerprinting, what we see here then is a very typical subduction-like sequence. Yet there's no obvious geological evidence for this. The evidence is for it being an intracontinental rift, and here we have subduction composition. So the obvious implication is that this is inherited from the previous subduction event. It doesn't represent an active subduction event. It represents a sort of inheritance from the previous one. So here's the idea then, long period of activity, from 3.55 to about 3.1 or 2.95 gigayears, plume to subduction and inheritance. And the same concept then, on the time, the same concept then can be used to identify hidden subduction events by looking at inherited subduction. In other words, looking at subduction chemistry from standard lips and saying from that chemistry, there must have been some more conventional, maybe arc-like subduction event older in the sequence. And this is a particularly good example, the Kopfel craton and the Bushveld, which everyone's heard about, large igneous province, strongly mineralized. And if we take characteristics of lips, which we see here, then the Bushveld fits beautifully into them with a very large aerial extent, a huge igneous volume, and a relatively limited lifespan. And it's the same in terms of its geometry. Lips tend to be much more sort of circular in geometry. Here it's about 600 kilometers across, as far as I remember. And so it doesn't have any arc characteristics. It's very simply a lip. But within it, there's a magma type, which relates to some of the chills in the Bushveld complex, but also some other lava units, which are quite distinct and quite abundant. And if we plot them on the same diagram that I showed you before, what you can see is, well, they're very like the Malina Basin. They form a AFC, assimilation fractional crystallization sequence, but there's no sign of any actual plume involvement in these particular rocks. They're much more like a volcanic arc type magma. And we see that here in the Scandium diagram as well. So the idea then is the combination of a clear intraplate, if this is plate tectonics, so a clear plume tectonic environment. Within that, we have example of subduction-like chemistry, and the only obvious explanation for this is that there's lithosphere in there, which has been injected with subduction-like material back in time, and this has inherited it. And it's not alone. Clausen and others have studied dike swarms of older age in the Kopfel craton, a couple of examples there. And we can see them here. I can't quite see that on my screen, but one example is 2.65 gigayears, the other is 2.95. And again, they relate to likely lips, but we'll see they have subduction signatures. So here's the geology then, the 2.95 here related to a dike swarm, which appears to emanate from the margin of the Kopval craton, and maybe two dike swarms for the 2.65 gigayears. So no indication of any geometrical volcanic arc or anything like that, just typical lips in an intraplate environment. But when we look at their chemistry, what we can see is that in both cases, which I guess you're familiar with by now, we can see that they have subduction-like components. There's no indication of any involvement of mantle plume in these. So again, they must be almost certain, I would say, to be inherited. And then how old are they? Well, here are the lips with their subduction signatures in the Kopval craton. And here to the right of this, which I can't follow on my pointer, but you will see that they extend through the Kopval craton, and even at 2.95, they're not related to active subduction. So either in this Dominion group, in the older part of the Dominion group, there's an arc, or there's an arc further down in the Kopval craton that can't be recognized in this particular section. And that's the essential idea. But perhaps I should just go back to that. But the key point is, in both cases, you've got a subduction event, maybe a single subduction event. It doesn't just create what might be a volcanic arc, it also leaves inheritance in the lithosphere, which can be sampled for a long period of time afterwards. I won't go into it, but in the Superior Province, a good example is that you have arc-like activity at 2.7 gigayears, and then the evidence of subduction influence on lips extends from that almost right through to the time when you get another orogeny at 1.9 gigayears. So the message is not to treat everything with a subduction signature of subduction and lots of subduction taking place. It's more an episodic event with rather rare but large subduction events followed by a lot of inheritance. That's what I would estimate it at. And then the question is, how far back can we go to identify subduction? And this has been cited as the oldest example, and so I've examined this in a bit more detail. Navragituk, and I've no idea if that's exactly how it's pronounced. Oh, my watch doesn't understand. But anyway, Navragituk in the Ungava Peninsula in Quebec, site potentially of the oldest subduction-like volcanic rock, indeed the oldest volcanic rock. But the problem is it's not very large, it's only 9 square kilometers, and you can see it's a very high metamorphic grade, it's upper amphibolite facies, and just to confuse things even more, it's been invaded by this pegmatitic material, which could almost certainly influence thorium-niobium ratio. So, and it's been written about, Jonathan O'Neill, who identified this and did the early work. He favoured some sort of subduction influence on it. Simon Turner claimed that this was the start of subduction on Earth. This was in Geology. I was invited to write a kind of reply to this, but there are no diagrams in it. I just kind of talked about what I talked about here, but in a paragraph or two. And pointed out, as I'll show you in a minute, that their data are quite consistent with what they propose, but one has to be just a little careful when looking at the oldest rocks, where there's been a lot of mobility. So we'll have a look at that. Here's the geology anyway. It's a syncline, as you can see here, and as a syncline then sorry, it's an anticline here, sorry. And then you've got the low titanium enriched samples, which are in red. You've got the low titanium depleted samples in blue. And then at the bottom, well, it is the syncline, sorry, you've got the high titanium lava. So you've got 3 different groups that have been identified. And here's where they plot on the crustal diagram. So you can see that the uppermost sequence clearly within this volcanic arc array. The other two sequences form a trend between that and the Moore-Boybe array here. They could be intraplate with crustal involvement. They could be back arc. There's a whole series of options which we'll have a look at. But in either case, O'Neill and Turner both recognize this type of characteristic as being a subduction characteristic, and the difference between this and this led Turner et al. To suggest that this we're looking at is subduction initiation. So let's just look at the problem, and the problem is that thorium has been metamorphosed, has been mobile, and so have a lot of other elements that are used in the fingerprinting, including elements which have isotopic ratios. And this is easy to see if one looks at small space scale variations. So in here, you can go for a sample here to a sample next door. One will plot here, one will plot there. And this is a very small area, so clearly they're probably the same lava unit. And so we are looking at alteration in this particular case. And the question is, can we see through it? Is this simply here because it's highly altered by thorium-rich pegmatites or whatever? Or is it representing real subduction-like chemistry? That's the question. And so we can see this problem here. As I say, we've got the pegmatites here, we've got the variably metamorphosed high-grade amphibolites here, and we have to somehow see through them. What I did for this was to look at experiments, and this is one from Kessel, a sandwich experiment. He's taken some crust, actually he's taken some sediment here, put it in a sandwich between different materials, and then the melt from these has been collected and analysed. And this is the results he gets on a range of temperatures here between 700 and 1,000 degrees centigrade. And I'm interested in the difference between the most mobile element and thorium, because that's going to be an indicator of, or a proxy for degree of mobility. And we can see it here. Here's cesium, the most mobile, is always strongly enriched, no matter what the temperature. If we go to thorium, at low temperatures, any degree of enrichment is small. As we increase the temperature, it gets larger and larger. And the consequence of that is, if we take cesium-thorium as a proxy for temperature, then that's going to, the cesium-thorium ratio in the rock is going to carry a record of what the amphibolite facies metamorphism is. And the question then is, can we use that to see through to what was happening before? So that's what I'm going to do now. What I did was to take my database of volcanic arcs, fresh ones, which was something like 36 different arcs, plot them as a 90% probability ellipsoid, and they, fresh arcs, all plot in this field here. I took more glasses and some OIB, and they plotted in a field here. I then converted that, taking a bit of extrapolation onto what the total variation might be, into this fingerprinting diagram then, which is similar to the one you've seen with scandium, but with cesium, niobium as an axis. So we've got the arc field, we've got the Moore-Boybe field. Cesium thorium is the proxy. So as you go this way, the value of the proxy is going down, which means your higher temperature. If you go this way, it's going up. So you've got more cesium, so you've got lower temperature. And so here are where the Navarrete compositions plot, and perhaps not surprisingly, they're all moving towards the vector, which is to higher cesium thorium, which is the consequence of lower temperature metasomatism. And we can see in them variations in thorium niobium, and that demonstrates too that thorium, as well as cesium, is mobile. So how do we interpret it? Well, what I plotted on here are the compositions of metamorphic fluid melt materials that are from these sandwich experiments. So 600 degrees. As we increase the temperature, so we get cesium-thorium ratio going down as more thorium is released, cesium being more or less constant. And so if we look in this diagram, I can't get my pointer across right to the end of it, but what you'll see is then that these compositions are essentially pointing towards a sort of metamorphic fluid in this sort of region. As I understand it, I didn't get the data in time. People looking at the metamorphic grade, the amphibolite facies temperatures, have come out with temperatures, peak temperatures of about 650, which would put us in here, which is broadly consistent with what we see on these diagrams. So the question is, can we extrapolate back? And here's the way in which one could do it. So what we have here then is the upper unit, the enriched unit, and this will be the direction of metamorphism then, going towards higher cesium. And we'd have to extrapolate it back along this diagram, and you can see it will finish up still in the arc field. Rather strangely, actually, during the metamorphism, thorium's actually going down as cesium's going up, and you can see that from the angle of this trend. The other two units, if you extrapolate them back on what look like to be alteration lines, you can see they would extrapolate back probably into the Morboid field, although you can't be absolutely certain they wouldn't sort of finish somewhere here, but nonetheless they appear to extrapolate right back into the Morboid field. These are two different metamorphic assemblages, this and that, so that they both plot back into that sort of field. So the consequence is then that if we extrapolate them back and look at what it might show, then the upper unit, just like in the Bushveld, just like in the Malina, just like in the arcs as well, or some of them, they form a trend right in the middle of the volcanic arc array. The two other units plot in the Morboid array as I've extrapolated them. I can't say they're not going to extrapolate here, in which they're going to be plume-like with added crust, but nonetheless they could, as has been proposed, represent pre-existing highly extended continental crust or oceanic crust upon which this unit has been emplaced. We can extrapolate them here using scandium, and we get exactly the same result. So the really interesting thing about this is that we've got the oldest rocks on Earth. O'Neill and Turner proposed that this relates to one of the earliest, if not the earliest, global subduction events. And they didn't take metamorphism into account, but when you do, it does seem to support it does support their model. What it doesn't support, and what the really difficult thing is, because we've got a 9 kilometre square area of rock with very little geological constraints, what we can't say is, was this like the Wundu sequence, where this is a true volcanic, what appears to be a true volcanic arc-like sequence? Was it, on the other hand, did it represent some previous event which provided a sort of proto-lithosphere which inherited subduction from something that was even older? And that's what we don't really know. If you ask me to take a guess, which is all it is, I would say that it is quite interesting that in the inherited sequences, typically basalts are dominant, whereas in what one would regard as more volcanic arc-like sequences, you get quite a range of compositions from basalts, andesites, and dacite. And here well, it's a very small area, but they are predominantly basaltic, and the very, very slight probability then that these may have been inherited from something earlier. However, there are other options, and we will have a look at them very briefly now. Let me just check the time. Good. Okay, so the outcome so far then is that I would argue that subduction in the broad sense, by which I mean recycling of crust into the mantle, and causing a mixture of input crust plus mantle to melt did take place in the Archean. Looking not just where I looked, but other areas, the episodes where this took place as a potential active subduction sequence are actually very rare. One in the Pilbara, one in Canada maybe, one in Cap Vert. They're not actually that common. And so models for sort of episodic subduction, I would say, are supported by this. What the evidence also is, though, is that one of these events can give you arc-like sequences for an awfully long time within the geological record, leading to a lot of subduction-like signatures in what are clearly lips with no subduction origin. So I would say, if one had to come out with some conclusion, it would be episodic subduction-like events which are sufficiently large to lead to inheritance of mantle lithosphere. And then the other point is that, of course, it's not my idea, but I support O'Neill and Turner in the idea that subduction in the broad sense can be traced back to Earth's oldest volcanic rocks. And I would argue maybe if they're inherited, it could be translated to something even earlier. So those are the outcomes. And of course, that's not the only thing. The question is whether these episodic events are volcanic arcs per se, or whether they're simply potential plate tectonic indicators, but maybe don't relate to, certainly not to global plate motions. And this is something, of course, I haven't really dealt with, but it's clearly a key point. So the question is, what can these processes be? If we take Navaragatuk, Simon Turner and others have produced a paper recently, and they don't dispute their original model, but they do talk about the possibility of meteorite impacts causing subduction in the early Earth. It's still subduction, but it's meteorite driven. So that's one option. So it's not plate tectonics, that's meteorite impact. Most other models, though, relate to delamination. So their argument is that we don't subduct continental crust from near the surface as a slab or a thrust unit, or whatever you want to call it. But what happens is the crust becomes unstable and delaminates, and that includes crust, and that then refertilizes the mantle directly underneath. So that's an option. I find it a little difficult to go from that to enrichment of mantle lithosphere, because you're actually taking mantle lithosphere away here rather than producing enriched mantle lithosphere. But it is obviously an option one has to consider. And we have Jean Bédar's and Harris's models here, which I actually like. And they would argue that you have convergence, which doesn't relate to plate tectonics, I guess. It relates to mantle flow, but causes convergence. And the consequence of that is to bring upper crustal material down into the mantle. It's not that different. I've exchanged a few emails with Jean, but it's not that different the way I'd see it, because I would see the early Earth as a lot of shuffling motions in which you have extension and the compression brings down parts of cratons that have been particularly thinned and therefore can get kind of subducted, or at least partially subducted. And so I would see little small cratons like this extending and then compressing, and that will give you a subduction-like sequence. This is rather different. But either way, it raises the question as to whether the subduction that I've been seeing does relate to a global plate tectonic process, or whether it does relate to kind of shuffling of whatever you want to call them, microcratons or whatever, giving you subduction-like processes, but without any global plate tectonics. So that is also interesting. I have looked at this in terms of geochemical modeling, and I'm not going to go into it because it's quite complicated and need another lecture, really. But it is possible to model what would happen when different materials go down into the mantle. And what I've done here is to take what estimate of mantle asthenosphere, an estimate of Archean mantle, and I've interacted it here with TTG type sediment. And you finish off with a reaction trend like this as you get more sediment input. If you take plateau-derived sediment, you come out with something like this. And one of my problems is if you do this for delaminated lower crust, which often has low thorium-niobium ratios and so on, very mafic, then you don't really get the sort of trend that would be needed to give you the examples that I've observed. So I do still think that you need some sort of upper crustal material to get in to explain what we actually see and what I'm interpreting as subduction and possible, but not definite plate subduction. So that's it. Just to go back to this and explain what I've done then in terms of fingerprinting, what I've done is to say that here's a flow chart, and this flow chart is looking for potential plate tectonic indicators of active subduction, inherited subduction, and oceanic crust, as opposed to processes which relate to lips or what you might call plume tectonics and don't have anything to do with potential plate type motions. I haven't had time to look at this one, but it's in the paper if you want to look at it. I've looked specifically at this one. So I've picked out samples then with high thorium niobium, which then give you potential subduction. I've ruled out the samples which might be due to plume crust interaction, and I've carried on to look at potential subduction. I then essentially used geology to decide whether that subduction is potential active subduction or potential inherited subduction by a later plume event. And I then discussed, but without necessarily getting very far, as you noticed, as to whether these active and inherited subduction events do in fact relate to something which is non-uniformitarian and therefore can be explained by something that none of us probably totally understand. And this is the methodology then I went through. I looked at the high thorium niobium ratio. I used the scandium to separate crust from crustal assimilation from subduction. I corrected for high-grade metamorphism, and I then distinguished true from inherited subduction through geological methods largely, and then looked at the distinction between crust and metasomatized mantle. So that's it. Thank you very much.
Thank you for the wonderful talk. Let's open up the floor for discussion and questions. If you'd like to, please raise your hand, or you can feel free to type your question into the chat. Our first question is Greg.
Wow, that was awesome. I love revisiting Pilbara, but my question is about the Quebec example. Well, you have banded iron formation, and the stuff immediately below it is enriched in titanium, which makes me wonder, could that possibly be a paleosol? It'd be good to have a sequence of analyses down from that basalt to banded iron formation contact and look not only at titanium abundance, but also zirconium abundance, because those are fairly stable elements in weathering profiles. This could be the oldest paleosol on Earth. I thought I had the oldest one in Greenland, but this would be quite a bit older.
That's a really interesting idea. I mean, zirconium data are available. Zirconium is a very sort of alteration resistant element. So it is something that could be looked at. I don't think anyone has.
Fascinating. Thanks for the tip. I'll delve into it.
Yes.
All right, John Bailey.
Julian, magnificent talk. I've always found your research very inspiring. As many will know, we're trying to play the same game with zircons, and
Yes,
to push it back into the Hadean,
yes,
where we have a lot fewer constraints, but perhaps one advantage that the ratios inside the zircon are a little more robust to metamorphism. We're
yeah,
seeing pretty much exactly what you just said. It looks like the subduction proxies, if we accept low niobium and high scandium as such, extend back to at least 4.2. And it appears that I use the word subduction just like you, the burial of shallow rocks uh, can be traced back that far. One thing I think you didn't mention was that if you are delaminating the base of the crust, those are rocks are largely at granulite phases. They're dry, so that doesn't do much to form granites. Whereas if you take surface rocks, it buries water. Uh, I was just a little curious. You use thorium over niobium, so I have a question: what you see if you use uranium over niobium instead, which is the common zircon proxy?
yes. I have looked at your and other papers on zircon fingerprinting, and I have I did notice that you have uranium niobium as opposed to thorium niobium, and it is an interesting thing. Of course, uranium is potentially mobile, but again, you can use sort of methods I showed to see through it. I would imagine. You've encouraged me to look back at. I mean, what one needs are one or two examples where there's the whole rock chemistry and the zircon chemistry and the fingerprinting, and be able to sort of compare the two methodologies, which I think it would be really
Yeah,
interesting.
exactly.
And I know you use scandium as well. I was quite interested in scandium in zircons, which not everyone analyzes, but it looks like quite an interesting element. So yes, and the granulite facies point you make is a really interesting one because a lot of granulite facies rocks in the lower crust are actually depleted in niobium. In zirconium. Sorry, I'm talking nuts here. Is depleted in thorium, and it's a kind of the opposite effect of metamorphism in amphibolite facies, really, because in the lower crust, when you have melting to remove volatiles and melt, you're taking thorium with it. And that thorium can then enrich the crust above, but meanwhile the lower crust is being depleted. So if you take the fingerprinting diagram I showed and plot a number of lower crustal examples on it, they plot below the Morboy array because of the thorium depletion. And you can work on correcting for them in the same way I showed, but instead of heading in one direction for increase in say thorium, you're going in the other direction to decrease in thorium. So it's quite a complicated thing. But I would certainly agree it doesn't actually favor delamination because what's in the lower crust is not really what is going to refertilize the mantle. And if it did, it wouldn't refertilize it the way we see. So I agree with you.
One other thing we can do with the zircons, I don't see other hands raised, so I'll keep going. Uh, it, we see quite different chemistry in the zircons from the Jack Hills than what Nadia Draben reports for the Barberton Hadean zircons, and we interpret that to mean that there really are quite a few tectonic environments operating perhaps simultaneously in the Hadean, and that these Hadean zircons are sampling a large amount of crust. It's not one little area that's feeding these zircons. The Barberton ones look much more mantle-like, much more like they're an ocean island kind of a plume
Yes.
source, whereas the Jack Hills have a much higher concentration of scandium-rich zircons and niobium poor zircons.
Yeah, the Barberton is there is less crustal input into some of the earlier plume-like magmas in Barberton. I think that's yeah, that is definitely true.
Oh.
One interesting thing to me, I mean, I've been very interested in the work that you and others have been doing on zircons. And yeah, it's one of the interesting things. If you take the whole rock, using scandium there, it was possible to extrapolate back from high thorium niobium in the evolved rocks back to what the basalts would be. And one could do that because one is also analyzing whole rock that wouldn't necessarily have zircons in them. So you can look at then the whole sequence from acid to basic, and the zircons, as I understand it, you're going to be up at the acidic end where the melts have been saturated in zirconium, and then it must be quite difficult to extrapolate back to what they would have been at a basic composition. Is that correct?
I envy you having whole rock data. I think the answer to this question will be looking more at the Archean samples, and we and others are attempting to do that now.
Yeah, and I envy you having 4.2 gig a year materials.
All right. Next question is Jean Bedard.
Hey, Julian. Good talk.
Hi.
I agree with most of it. But the question I want to ask is what's on screen. If all convergent margins are called subduction zones, then the term is meaningless, right? Which is why I suggested we make a distinction between a convergent margin where the lower plate is the active tectonic agent. It's the plate moving force, it's forming an arc, da da da. But what happens if a continent moves a bit, you shove the Abitibi under it, it's going to degas, it's going to get metasomatize the mantle, you'll get exactly the same signature, but it's not a plate driving force. So I don't think we should call it subduction. I think we should call that subcretion or something like that. Because if you say subduction when you mean subcretion, Joe Blow reads a paper. Oh, there was subduction, which means there were arcs. Everybody makes that equation in their head if we use the term subduction. So I think we should be really careful about what words we choose to describe this process.
Yes, I'm happy to discuss this one. I mean, as I see subduction, it is basically the transfer of upper crust and what's below it from near the surface into the mantle. And at least from the magmatic point of view, then contributing to mantle melting and giving you whatever you see. But the subduction process, I suppose, as I see it, is really doesn't have to be. It doesn't have to be a plate or anything. It's just something that brings crustal material down into the mantle to a point where it can refertilize existing mantle or create magmas. That's how I see it. So I would see, okay, there are various types of subduction, but they're still subduction. And what you were talking about, I kind of agree with you, see, because I think that some of the inheritance one sees may not actually come from a volcanic arc, something that formed a volcanic arc at all. I think some of it might be short sequences of subduction in inverted commas, which essentially bring the material down not into a mantle wedge, but above the mantle wedge, and therefore you refertilize what's above it. So I'm happy to sort of distinguish different types of subduction, and maybe one should call them different things. But it's at least with subduction, you're talking about something that's come from near surface down into the mantle. And then there are all sorts of different consequences. Whereas if you give them different names, then you have to kind of have a greater interpretation of what you're talking about.
Well,
I think that's a bit dangerous.
The tricky thing about that in the deep past, I mean, your approach works, right? But show me the arc, right? You go back in the deep past, I never see the volcanic structures and timing and geometry you expect from a normal arc. So in the deep past, for me, subduction means the presence of an arc because that's the only thing we can detect in the geological record. Whereas the underthrusting, well, you don't really see an arc. You see distributed metasomatism, matachites, which is what makes sense. So I see a fundamental difference, and I think it's worth specifying. If you want to call it passive subduction, I think that's awful, but it's better than just calling it subduction.
I mean, the other bad term, if you want to talk about bad nomenclature, is volcanic arc. Because that implies that it's an arc-shaped volcanic sort of edifice, or whatever you want to call it, and that it's got some distance to it, and obviously in the present day there's magmatism above subduction zones, which doesn't have arc-like geometries. And almost certainly in the Archean they didn't either, but perhaps certainly in the Archean they didn't either. So that's a misleading term as well. And if you've got microplates and so on, you might just have a volcano or two. And you're right. I'm calling it a volcanic arc, and it's probably wrong.
I don't want to
But that's another
monopolize.
nomenclature issue.
Yeah, I don't want to monopolize the discussion. I just want to make one last point. Where you look at the calc-alkaline sequence in places like the Abitibi or the Northeast Superior, even without seeing the shape of the arc, there's no well-defined volcanic front and core zone or whatever. It's stochastic. It's everywhere. It's not a well-defined belt. They don't exist.
Well, let me give you an analog from what I was doing in ocean drilling then, because I've been drilling what are essentially proto-arcs in the Western Pacific, and they form just after the start of subduction, as you know, related to rollback and the end of rollback and the start of arc volcanism. But what's been subducted by that point is not really very much. And if you then were to stop subduction at that point, equally, you're not going to get a volcanic arc in the conventional way. And one of the arguments in the paper with Mike Brown and co. is that what's happening in the Archean is actually what's been subducted are just very short length, thinned continental or maybe oceanic lithosphere. So you don't really get very much subduction. That also relates to the metamorphism, which was one of the points of the paper, because if in the Archean you have short subduction events, then the metamorphic grade for these, because subduction is starting beneath hot mantle, it hasn't had time to cool down, then you don't get blue schists or eclogites, you get amphibolites. If you then say with time, you get greater sort of separation of what is going to be an ocean or thinned continental crust, whatever. If you've got more material being subducted, then what's going to happen is that the subduction zone will have time to cool down, and it will then be possible to produce blue schist facies metamorphism. So one explanation for this, there's no blue schist facies in the Archean, could simply be that everything is a short-lived subduction event, maybe or maybe not related to some sort of global plate system. So in that sense, I like your diagram with the small sort of cratons or whatever it is and convergence between them, because I think that fits quite nicely with what you see. And maybe that's why you don't get the sort of arc sequences you might hope for.
All right. We have an additional question in the chat. If the Bushveld complex records an inherited subduction modified mantle signature, what tectono-magmatic mechanism produced the Bushveld magmatism?
My view would simply be that what has happened is you've got a mantle plume has impacted let's say it's just impacted continental lithosphere. It's undergone melting, and the heat related to that has melted the part of the lithosphere which has a subduction signature, and that subduction signature is then recorded in the magma that comes from it, and that gives you a kind of inherited subduction signature for those magmas. The way I actually see it is that in some places the plume rises and doesn't get to a point where it melts, but it's got enough heat in it to melt the enriched parts of the lithosphere, and that will give you the B1 type signal. Elsewhere in the craton, where the crust is thinner, the plume will rise further and it will melt to give you more sort of plume-like magmas, which then interact with crust and give you a different geochemical signature. So it's all a matter of the impact of a plume against mantle lithosphere, whether the lithosphere is thin enough for the plume to melt, and whether, if it isn't, there's enough heat to melt the lithosphere above. So that's essentially the idea. And you see that sort of pattern in a lot of large igneous provinces. So that there are many examples in the Superior Province, for example. So it's very common. The Bushvelt's just a very famous example where you see it.
All right. Thank you very much. Any other questions?
Yeah, maybe I ask Julian just two questions, or maybe for clarification. So you infer episodic subduction based on sort of a couple West Australia and northeastern Canada, and I'm just wondering, you think you call it episodic because you have other examples where you don't see evidence of subduction, or do you think there is a bias because that's all record we have, and like if we would have more examples, it would be not episodic in this case? Can you expand on it?
Yeah, it's a good point, of course. The number of examples are quite limited. But, I mean, it's not that different from what we get at the present day, in fact. I could give you an example. Let's take Canada. You've got it. There are lots of people here who know more about this than me, but I mean, this is how I would see it. That at around 2.7 gigayears, there's an event which brings crust into the mantle somehow, and at the same time metasomatizes that mantle. So you've got a subduction event at that time. In my definition of subduction, you've got a subduction event at 2.7. Then you get recycled. That event recycles at a whole series of episodes between 2.7 and eventually, when oceans have opened and closed again, eventually 1.9 gigayears, okay? Then after that, there are some places, Basin and Range in the States, a good example, where mantle has been metasomatized at 1.9 gigayears, according to isotope records. And then subsequently, plume extension gives you renewed magmatism 1.9 gigayears later, but it's still got the subduction signature from that episode 1.9 gigayears ago. And I think you can find other examples at the present time, if one looks for them, where you've got inherited magmatism that has gone on a long time after a subduction event, and then only finishes when there's another orogenic event which kind of superimposes on it. So in a way, I would say that what we see in the Archean isn't that unusual. I mean, it's a Wilson cycle effectively, and in a Wilson cycle, you'll get extension, you'll get convergence, you'll get collision, and then it'll open again. And when it opens again, you'll get renewed subduction, and these will be separated by a significant period of time. So as I see it, in a way, it's a sort of Archean Wilson cycle, the one seen. But I do agree, there's not many examples. So it's definitely a hypothesis.
So by episodic, you mean episodic on a scale of craton or block rather than episodic on a scale of whole Earth, right?
If it's whole Earth, it's a really good question. That if it's whole Earth, then one would have to see whether there were between craton sort of arc-like signatures at the same time. So I didn't go into it, but I would perhaps argue that the event in the Pilbara at about 3.15 or whatever GA, where there's the subduction event that gets repeated through time, then the one in the Kopfau is probably or potentially a similar sort of age, so that there might be a matching between those two cratons. Similarly, 2.7 gigayears in Superior, and I accept there are lots of people there who know more than I do, but I think that's pretty similar to events in Australia. So that it's really a question of matching ages to these subduction events. If they're all random, then clearly there's no connection on the Earth. But if on the other hand, they happen at particular times, then there is likely a connection. And John Valley on zircons, it's one explanation for the modality of zircon ages is that they concentrate at the time of these, what I call subduction events. And that produces a lot of zircons at that time that then get kind of recycled. There are sort of pieces of evidence, but it is in the world of speculation. I kind of agree with that. Yeah.
All right. And just, I'm not petrologist, but I'm curious. So you use scandium in Archean, and you prefer to use nickel in younger. Why wouldn't you use scandium also for younger magmatic rocks? What's the advantage?
It's a very good question. I do use them for arcs, actually. I do use them for younger rocks for arcs. But the reason is for modern rocks that nickel, because it's concentrated particularly in olivine and other mafic minerals, nickel decreases very fast in basic rocks. So it's a really good indicator. If you've got a lot of basic rocks, it can tell you very nicely whether those basic rocks have been interacting with crust. Scandium doesn't do that very well for basic rocks because its concentration is mainly in clinopyroxene, not olivine, and so it doesn't decrease in a very systematic manner. On the other hand, at the present time, you can get to quite low nickel values before you get to evolved rocks. And that means your evolved rocks don't show much variation. And so nickel isn't desperately good for comparing a sort of dacite and an arc from a basalt. In the Archean, unfortunately for me, the amount of nickel in magmatic rocks, in basic magmatic rocks, komatiites and so on, is so large and variable that it's very difficult to exactly work out what's going on. So you could have a magma chamber, and if it's being refilled by komatiitic magma or something like that, that carries a huge amount of nickel, and it will just mask any contamination. So that's essentially the problem. I think ideally one would like to use both. You'd like to use nickel for basic rocks and scandium for interpretation of the more acidic ones. But in the Archean, that's difficult. There are lots of papers on this, Claude Hertzberg and what have you. I mean, he's calculated the nickel content of komatiites and basic magmas in the Archean, and they're thousands of parts per million. If you go to present day, for the most part, they're in low hundreds of parts per million in a primary magma. So it's an enormous difference, and it tends to mask everything. It even gets into the crust. So if you've got Archean crust that's invaded by magma, that crust will finish up having a ridiculously high level of nickel. So it's very, very difficult to deal with.
Julian, if I could just jump in, I agree with everything you just said. But as you pointed out, zircons look at the more felsic end of the rock spectrum, and the scandium works very nicely in the Phanerozoic. This was shown by Craig Grimes and others 10 years ago.
Yes.
And so we use it for
Yeah.
zircons as a proxy.
Yeah, I use it. I haven't published it, I don't think, but I use it for arcs, scandium in the Phanerozoic. It's very effective. And in fact, you saw it on the diagrams I plotted, that the arc examples I showed had a really nice correlation with thorium, niobium in the acidic rocks. But yeah, I do envy you having the zircons. Yeah.
All right, Alexander Sobolov, you have your hand up?
Hello, Julian. Very nice talk.
Oh, hi.
Yeah. So the question, you didn't mention at all plume-induced subduction models. If plumes can induce subduction, that is ideal episodic subduction events. In our recent papers, we are trying to apply that for Hiddean, and it looks like it may work. Also for zircons as well, as John showed in their very recent paper. So why not plume-induced subduction?
I've nothing against plume-induced subduction. In fact, in the Western Pacific where I was working, there is a correlation. Well, there's the age of the mantle plume in the Philippine Sea Basin is at about the same time as subduction starts. So that there are these time correlations. But I suppose what I point out in the Archean, if you take the Pilbara, for example, you've got about 350 million years of plume activity without any subduction at all, apparently. So there you have a lot of plume activity, but it clearly isn't essential that plume activity will create subduction zones. And maybe that's an Archean thing. But you certainly get, and yeah, even in the superior belts, you get plumes with subduction signatures and so on, but you don't get obvious active subduction related to them. But that doesn't mean that your examples don't work, because obviously it can initiate subduction, as in Panama and so on. Yeah.
And actually, modeling show that maybe more significant feature of very hot mantle and crust. This kind of plume-induced subduction as our model in nature communication of Steve Sobolev, which was published last year.
No, that's very interesting. In fact, it takes me back. I wrote a paper with Yaoling Niu a long time ago. Well, he wrote it, to be honest. I didn't contribute that much. But he pointed out the potential relationships between plume and subduction, in the sense that if you have a plume creating a plateau, that there are deviatoric stresses, if you like, between that plateau and adjacent oceanic crust, which can lead to subduction taking place. So what you say, does make a lot of sense. It's just I don't really see any obvious examples of it in the limited knowledge I have of the Archean, because I see in the Cobfile and the Pilbara and so on long periods of subduction activity without any obvious subduction taking place. But maybe it does depend if you've got ocean crust around. If you've got no ocean crust, as there may not have been, then maybe it's not possible to initiate subduction.
Yeah, if it is continent there, probably it is not easy.
Yeah. But it is interesting, though, the relationship between the two, and certainly people have pointed out that subduction initiation, mantle plumes have an effect on it. Yeah.
Thanks.
All right. Any other questions? Going once, going twice. All right. Thank you for a wonderful talk, and it was wonderful. And if I think that's about it. So thank you very much.
I think
Great.
Paul had something. Paul,
Thank you. It's great to see some people again I haven't seen for a while. Nice to meet you again.
Paul?
I was just going to say that I think it's difficult to differentiate or distinguish between subduction and mantle flow because subduction induces mantle flow. And this was pointed out already in the 1960s by Walter Elsasser, that when you cool the mantle with slabs, the mantle cools and sinks, and that induces a mantle flow. And the evidence of that is that back arc basins are systematically deeper than main ocean basins of the same age. And that's because of mantle suction, as Elsasser called it, a suction due to the mantle downflow induced by the subduction itself. So
yes, it's the idea of cold spots and hot spots. Yeah, that's a good point.
So
I think Jean's right. Really, the nomenclature is very sort of ambiguous in a lot of cases, and I don't know how one deals with it, but it is true that there are a lot of things that one word is being used for a whole pile of different processes, and it is confusing. I couldn't agree more, really. Yeah.
Karl Popper said, "Don't get involved in arguments about definition."
Yes. Yes, that's why I call everything subduction. It makes life simple for me. Yeah.
All right. Thank you very much again.
Thank you, and thanks for setting it up.
Thanks.